Okay, hello everyone. This is our fifth meeting, and today we are covering acceleration methods for diffusion algorithms. I'll start with briefly motivating the need for this acceleration and then diving into several subchapters where we discuss various options of acceleration. So this is our story. Here is a drawing I borrowed from a paper by Xiao that was published in 2022. And in this drawing, he says the following. The authors say the following. What is it that we are after with generative models for images? We would like high quality samples. High quality samples, that means for us good looking images, which is just to say that we need high precision. We need those images generated to be such that they cover the whole visual spectrum. And this means good recall, excellent recall. And we need both as fast as possible. And so, as it so happens, GANs are excellent in producing fast images, and they are of high quality, but they are often suffering from mode collapse, which means that they are not giving us the coverage we are after. VAEs and normalizing flow are fast as well, but they are not providing high quality samples. And diffusion, as we have seen, are excellent in both precision and recall, but they are quite slow. Think about it. We are looking at algorithms that require, roughly speaking, 1,000 activations of a denoiser. It takes a long time, much longer than a typical single network that will produce an image with GAN or variational autoencoder. So something needs to be done here. And so 2 years ago, people started looking at this question and came up with all sorts of directions on how to speed up diffusion algorithms to make them competitive with GANs and the other tools while maintaining their excellent performance. So this is our story. We'll start with something called DDIM, Denoising Diffusion Implicit Models. It's a beautiful paper, quite involved one. And what I've done here is to create a description of it that the authors, I'm sure, will not love, but this is the explanation that I believe capture the story of what they are conveying. And yes, it provides a speed up of diffusion. We'll talk about how to combine denoising diffusion with GANs, a specific paper that did so with a lovely concept and beautiful results. We'll talk about nested diffusion. This is the work of Noah Melata. And we'll talk about other acceleration techniques towards the end. So this is our plan for today. Let's start. Okay. And of course, stop me anytime with questions. Let's talk about DDIM. This is the paper, brilliant paper that came from Stanford University, the team led by Stefano Ermon. The students doing this work are Jiaming Song and Chenlin Meng. We have already seen papers by Ermon and Song, but it was a different student. It was Yang Song. This is Jiaming Song. And so these two students have been doing their PhD with Stefano Ermon almost in parallel. And what we see here today is the fruit, one of the fruits of the PhD of Jiaming Song. Terrific paper, brilliant, and truly a revolution. And why? Beyond the fact that it does provide a speed up for DDPM. I remind you, DDPM, Denoising Diffusion Probabilistic Models, this is the algorithm we discussed last week. So beyond the substantial speed up that we will see, it has additional merits. For example, it is offering a very strange non-Markovian forward process for the creation of the chain of images, which is quite different from what we are used to think. Another thing is the fact that they're offering a deterministic diffusion algorithm. What does it mean? I remind you, in DDPM, we kept injecting noise within each iteration. DDIM can work without it. And so all the steps done are deterministic. You start with noise at the very beginning, and then everything else is just deterministic, which creates a new language of that tool. In fact, instead of talking about stochastic differential equations, SDE, you move now to talk about ODEs, ordinary differential equations. And there are other benefits, the ability to interpolate between images, etc. We will see all this. So let's start and see how DDIM suggests to attack the diffusion process that we are so much interested in. Okay, so instead of jumping straight to DDIM, let me go back and remind you of what we did with DDPM, because we will have a complete picture of what DDPM had in mind, and then we will see how DDIM changes it. Okay, so here is a quick recall for the things we did last week. DDIM relies on the very basic relations that says that incrementally we are moving from one image to the next forward from xt minus 1 to xt using a Gaussian distribution conditional that basically mixes the existing image with noise with proper weights governed by beta. This was the first step in this process. Almost immediately we recognized the idea that you can actually make large leaps from x0 to anywhere forward by yet another Gaussian, simply a Gaussian that accumulates the incremental noises that we had before. And now you are governed by the alpha t. Alpha t is the accumulation of the multiplication of those 1 minus betas. And so if you want to move from x0 to x70, there is a formula for it. And in fact, the conditional is a Gaussian. Wonderful. This was step number 2. Then we started looking at the question of reversing the process. We wanted so much to put our hands on the reverse probability that goes from xt to xt minus 1. What is it? What is this conditional? Why did we ask this question? Because we realized that answering this question will arm us well in order to sample from the probability of x0, because then in a chain of operations, we can get x0 samples. We couldn't do it. We got stuck here. We tried base and we got stuck. So what we did instead is to come up with a strange extension where we assume that x0 is known. So this was the third step. Add x0 is known. And now just use base, and we have done it. Use base. The reverse is the forward with proper multiplication and division. Simple base. And then we realize that all the ingredients here are Gaussians. This is Gaussian. We have just seen it before. This is the Gaussian that jumps from x0 to xt minus 1. This is a Gaussian that jumps from x0 to xt. This is also a Gaussian. In fact, it is a Gaussian, and furthermore, you don't need the x0 here because of the Markovian nature of the forward, knowing xt minus 1 is enough to know about xt. You don't need to know x0. So this was our fourth step, knowing that x0 doesn't belong here. And now 3 Gaussians, and we have an expression for this, a closed form expression. And what is it? We developed it and found out that this is the expression. Looking at it is a Gaussian. It's a Gaussian of the variable xt minus 1 with some mean and some variance times identity. The variance itself is very easy, simple constant that computes itself from the parameters we have. This expression here is combination of xt and epsilon t. I remind you, epsilon t or x0 are interchangeable. One indicates the other because xt, x0, and epsilon are connected this way. So it doesn't really matter if you write here epsilon t or x0, same thing. Lovely. So we had this expression and we started thinking, what can we do with it? And the idea was that the reverse probability that with which we will sample should be as close as possible to this one, to this expression, so that eventually p theta of x0, the learned probability of images, is matched with the true probability of images. So the message was, make p theta of xt minus 1 given xt as close as possible to this expression. Here it is again, okay? So we are making the two as close as possible, and then we made an assumption. The assumption was, p theta, let's assume that you are Gaussian. And there are some justification for it. So p theta is a Gaussian. Now, a Gaussian wants to be very close to a Gaussian. All you have to do is to match the moments. Copy the second moment, S is, and since the first moment involves epsilon, so replace it with epsilon hat or x0 hat. Basically, apply a denoiser. This is what we did with DDPM. Here is a summary of the chain of rationale that took us one step at a time all the way through the steps I've shown you in order to create the eventual algorithm. We started with a Markovian incremental structure that goes forward one step at a time. Very simple. We realized that it can be replaced with large steps that go from x0 to any xt. We wrote the reverse, but knowing x0. It's a compromise versus what we really need because we don't know x0. Then we realized that with the base rule that replaces the order, if you go forward and know x0 or doesn't know it, it doesn't really matter. So this is an observation that we relied on. With 4 and 3, we eventually got an expression for this conditional, reverse conditional. And then we stopped for a minute and said, P theta, let's assume that you are Gaussian. And then with the assumption that it is Gaussian, step number 6, and with the closed form expression that Q has here, we merged forces and came up with P theta eventually. And P theta is basically the very same Q with one change. Replace x0 with x0 hat, and this is DDPM. Okay? Questions so far? Okay, so now let's introduce DDIM. The structure will be somewhat strange to you. Be flexible and accept what's about to come. Okay, so DDIM start here with stage number 5. DDIM says, you know what, I'm going straight to this reverse probability, and I'm going to suggest an expression for it. Here is the expression. Trust me, it's a good expression. And you think to yourself, my God, what were they thinking? Where is it coming from? What is the intuition behind this strange looking expression? So let's give a little bit of intuition and then proceed. So here is the intuition. Here is the expression again. And I would like to draw your attention only to this expression here. What is it? Think about it. We do have this connection in DDPM that says that every image xt is a coefficient alpha t square root alpha t times the clean image plus 1 minus alpha t square root times the noise that is added. And so this expression is nothing but this epsilon. So if you know xt and you know x0, this is an attempt to extract the noise in xt. Okay? So this is epsilon, the noise that exists in xt. Now, let's now look at the broader expression. What do we see here? We see here square root of alpha t minus 1 x0. Square root of alpha t minus 1 x0 plus, forget about this sigma for a minute, assume that it is not here, plus square root of 1 minus alpha t minus 1, the very same epsilon. And so it is a formula for xt minus 1. So it makes a lot of sense that you extract the noise from xt and recreate a combination of the noise and the image to create the next image going backward, xt minus 1. So this is the rationale here, or some intuition about it. And now we have this sigma t here. If you take sigma t here, and it is obviously a positive value, you basically reduce the effect of the additive noise that you have here. But you inject it back using an independent noise that comes from the outside. This is sigma t here. And here, look at something really, really strange that happens here. Sigma t is a parameter, and we will be playing with it. It could be anything between 0 and 1 minus alpha t minus 1, so that this doesn't become negative. And when sigma t is 0, we are coming back to the interpretation we have given with an amazing consequence. Sigma t 0 here means, what does it mean for this Gaussian? What does it mean?
It's the delta function, Dirac function, sorry.
It's a Dirac function, which basically says there is no probability density function here. Just compute the mean and that's it, right? So it will be the deterministic part I mentioned before. So this is the story of sigma t, and we'll come back to it. So this is the expression they suggested. In fact, what they suggested is something broader. So let me now take you to the broader picture of what they suggested. They said the following. If I want to define the forward process, then I need to show you how from the clean image, I'm creating the whole chain of images. And they wrote this expression. The green parts are exactly the ones we have seen before. This is the expression I kept talking about. This is the green part. And then there is the yellow part that says xt, x capital T, is created from x0 using this formula, which is, by the way, the formula we are accustomed to. Basically a mixture of the clean image and noise, where the clean image is hardly there because alpha t is nearly 0. Okay? So this is the proposal. Now, if you look at their proposal of how x0 creates the complete chain of x1, x2, x3, all the way to x capital T, you'll see something really, really strange. It doesn't look like a forward process at all. So how does it work? So let's illustrate it. Here's the expression again. And here is how it really works according to their formulas. It says the following. This is the chain. You are given a clean image. Remember, in the forward process, we are given a clean image and we are creating the complete chain of images that are more and more noisy all the way to the point where XT is simply just noise or nearly just noise. Okay, so how are they created? Based on this formula, here is what you're supposed to do. From X0, you're supposed to create XT using the yellow part. Okay, with this conditional, you know how to draw XT. Given XT, X capital T, go to the last element in this multiplication and now create X capital T minus 1 given the XT and X0. So knowing XT, you move down one step, but with the help of X0, and so on and so forth. So basically, this forward process is not really forward. It's some sort of backward, but it is causal in the sense that if you have a clean image, you can create the complete chain. Let me stop here and make a comment. We are just making mathematical assumptions. It's not that the algorithm will be necessarily influenced by this. This is just assuming how the diffusion worked in the forward in order to give birth to the backward. And at the moment, we are going with the suggestion that they are making. Okay, good. Here is the first implication of what we have just said. Remember, this is the expression we have written. And the claim here is that for DDIM, the probability of XT given X0 is this expression. It's a Gaussian. It's a mixture of the clean image and noise with these coefficients. If you think about it, this is exactly what DDPM has. So by a miracle somehow, despite the fact that all the proposal is very different from DDPM, these conditionals that go large leaps from X0 to any XT are sharing the same structure. So what am I telling you here? I'm telling you that step number 2 in our drawing is just as correct for the DDIM as it was for the DDPM. And the immediate consequence, and this is a great thing to have, is that the denoiser that you have for DDPM is exactly the denoiser you want to use for the DDIM. Why? Because what is it saying? It tells you that XT is a noisy version of X0 with a proper scaling down of X0 and additive noise, Gaussian noise. If you want to denoise, you have to go with this equation in order to go back from XT to X0. Well, it is the same denoiser because this property number 2 is the same for DDPM and DDIM. Great. Okay, let's move on. In fact, let me talk about proving this property. How do you prove it? It goes like this. Here is the claim. The claim is that those conditionals are plain Gaussians of the form we have seen. And I remind you, here is the assumption. We have seen it before with the yellow parts and the green parts. Those are the reverse conditionals that keep knowing X0. And this is the jump from X0 to XT. And I remind you, look at the yellow part here. The yellow part is exactly what this claim says for time step T equals capital T. So at least for capital T, it is correct. And so you can guess what I'm about to do. You assume this for T. You know this for capital T. You assume it as induction assumption for any time T, and you want to prove that it applies to T minus 1 just as well. So let's now prove that for T minus 1, this is also correct. How do you do it? Here is the idea. This probability, this conditional X T minus 1 given X0 can be written with marginalization. Look at it. This is this expression of xt minus 1 given x0, just like here, but also given xt, multiplied by all the xt's given x0, and then you integrate over xt. This is marginalization in its classical form. And by doing that, you end up with this probability that we are so much interested in. Now, let's have a look. Q of xt given x0. What do I know about it? What do we know about it? Q of xt given x0.
It's a Gaussian.
It's a Gaussian, just because of the induction assumption. Okay, what do we know about the Q of xt minus 1 given xt and x0? What do we know about it?
Also a Gaussian.
It's also, this is the very first equation I've shown you for DDIM. This is the assumption. They insist that this is the connection between xt minus 1 to xt and x0. So a Gaussian and a Gaussian integral. So basically, we are convolving two Gaussians to create something that will be what? What will it be? It will be a Gaussian. Okay? And so realizing that this is Gaussian, you do the integration, you do the nasty algebra, and you end up with this connection. And I'm not going to do it. And so this is the proof, or at least the sketch of the proof. So great to know that DDIM shares something in common with DDPM, and this shared part enables us to use the very same denoiser. This is good to know. Proceeding. Let's proceed. So from 5, we got to step number 2. It's just as correct as the DDPM. Now I'm going to do something strange. Look at this formula here. This is the base formula, and it is exactly the opposite of what we kept doing in the DDPM. In DDPM, we had the forward, we had the forward. This is the forward from xt minus 1 to xt, and we moved to the backward using base. Here I'm actually doing the reverse. And why? Because I already hold the reverse. So given the reverse, I would like to tell you something about the forward. Classic base. Put aside the fact that x0 is known in all the ingredients. What you see here is probability of xt given xt minus 1 is the reverse probability times the probability of xt divided by probability of xt minus 1. Great. Now look at this expression. Probability of xt given x0, what is it? What is this?
A Gaussian.
It's a Gaussian, just because of the previous theorem. The same for this. So the Gaussian here, and this is another Gaussian, a Gaussian that we have defined at the very beginning. So multiplication of 2 Gaussians, division by yet another Gaussian, this is Gaussian as well. So in fact, I can come up with an expression for the forward that will be a Gaussian, okay? And here is a claim, and the claim says, you know what? You can do that, and go ahead and do it. But x0 is not going to fall out. It's going to stay here. You need it. What does it mean? It means that the forward that emerges from their assumptions is not a Markov chain anymore. You cannot move from xt minus 1 to xt unless you know x0. Okay? And how do you prove it? We'll say it in a minute again. I'll mention it now. You just go ahead and compute those multiplications, and you get an expression. And if the expression has x0 in it and it doesn't vanish, you're stuck with it. And that's it. Okay? So, in fact, this means that step number 1, the very first step that says, here is a Markovian chain that moves from xt minus 1 to xt and using simple Gaussians, it's not true anymore. And the step number 4, that assume that you can omit x0 from here without any harm, this is not true as well. Okay. So this is something that needs to be clarified here. Again, we don't care really whether it is Markovian or not. It's not going to hurt us in any way. It's just the assumptions that talk about how the forward process is happening. And why? Because then we can give birth to the reverse process, which is the part that is being truly computed. Okay, so with this forward, here are the implications. If you do compute this, now I can give you another way of computing all the xt's from x0. Imagine that you have x0 and you want to create x1, x2, all the way to xt. Before we had one way of doing it. Here is another now. From x0, create x1 using this equation. Lovely. From x1 and x0, create x2. From x2 and x0, create x3, and so on and so forth. So x0 keep injecting its knowledge in order to help the creation of the next vectors. And this is how the forward pass can be computed. Okay? Can be computed, doesn't have to be computed. Good. And again, just for the sketch of the proof, how do you prove that x0 is here to stay? You just do the algebra. 3 Gaussians, do the algebra. If you care about it, just use it as an exercise, and you'll find out that this is indeed a vector that stays here. It doesn't move out. Okay, so 2 claims. So let's summarize. We started with step number 5, with a specific choice of Q that goes backward with the knowledge of x0. We have seen that it implies step number 2 that says there is a connection between every xt and the clean image as an additive noise, and therefore the denoiser is the same. We saw that we can compute the reverse of this, which is the forward, with x0 as known. But unfortunately, you cannot remove x0. It's here to stay. It's not Markovian. And this is applicable also for step 1. It's not Markovian. And we don't care. It's nothing that we are to be worried about. And the question is, how do you proceed now? And the answer is almost the same. Here is what you do. Now that you know this equation, assume that p theta is Gaussian, and make it such that it is closest to this one. How? By matching the two moments. Copy the variance, because it's just a number. And copying the mean imply that you refer to x0 as something that you can take from a denoiser, and that's it. And this is your DDIM. Great. So what? What just happened here? Where is this wisdom in this algorithm? So let's talk about some consequences that will highlight what DDIM brings to the table that didn't exist before. Okay. So few consequences. First, you have a parameter and you can play with it, sigma t. Anywhere between 0 and 1 minus alpha t minus 1 is a valid choice of sigma t, and you'll get a family of algorithms, and now you can compare them and see which performs better. In fact, if you choose sigma t as this value, I didn't prove it to myself, but this is what the paper claims, then you fall back to the DDPM. So DDPM is in fact a special case of this algorithm. Lovely to know. But the more interesting case is where sigma t is 0. This is the promoted version. This is DDIM as people are practicing it in the most common way. Sigma t equals 0 means that the coefficient here is simply square root of 1 minus alpha t minus 1, and there is no noise. So basically the computation, they take you all the way back, do not include injection of noise. And so the algorithm becomes deterministic. Another consequence of this, if it is deterministic, something happens that can help us interpolate between images. I'll show you in a few minutes what I mean by that. So these are almost, I would say, the immediate consequences. Here are the more sophisticated consequences, and one of them has already been mentioned. The fact that step number 2 is the same means that we can use the same denoiser. This is great. It's horrible to reinvent a new denoiser and then try to train it, etc. So no, just the regular denoiser that we used for DDPM. And the main consequence, turns out, the DDIM can use only few steps in order to achieve good quality image synthesis. 10 to 50 steps and you get good quality images with low FID, as we will see in a minute. Why? Where is it coming from? Nothing here spoke in terms of speed up. So how suddenly we got this speed up effect? Two possible explanations, and we mentioned them both. The first is the non-Markovian nature of the forward path. Being non-Markovian means that x0 keeps injecting itself in the forward, and therefore it carries information that in the reverse help us. But I think the main reason is the deterministic option. The deterministic option, the one that refers to sigma t equals 0, basically moves from SDE to ODE. And here is what happens. The path of vectors that migrate from x0 all the way to xt create something much smoother, and therefore you can coarsely sample it without any harm. And this is exactly what DDIM does. Instead of sampling 1,000 steps, tiny little steps, it samples crudely and still performs very well. And so let's see some results to illustrate how it works. Here is a table that shows some FID results. All of these are FID results here and here for two data sets, CIFAR10 and Celeb A. Okay. Now there is a parameter here, eta. Eta is a parameter between 0 and 1 that multiplies this coefficient. I remind you, this coefficient is exactly the value that DDPM will use. So if you choose eta equals 1, this is DDPM. Okay, if you choose eta equals 0, you are in the deterministic version of DDIM, the one that doesn't inject noise. There is a paper in 2020 that did DDPM with a different choice of sigma that was much higher, and they squeezed excellent results for 1,000 steps. So we will compare to this as well. So let's start with DDPM, the version from 2020.
Mickey, can I ask a question first?
Yes, please.
Regarding the equation in the previous slide, if you can go back to it just a second. Here, are we specifically using x0 as in the input image, the clean image, or can we use like x1 or x2, meaning any previous image in the step?
This formula mixes xt and x0. When you do the reverse, you don't have x0. So what you do is to take xt, feed it into a denoiser, get x0 hat, and stuck it in. Is it clear?
Yeah, so x0, like x1 doesn't hold the same information as x0, so therefore x1 will not help us because you
No,
said that
and you don't, if you don't know x0, you don't know x1. Why are you going to x1?
Yeah, just to make sure that I understand, by you saying that it's not a Markovian chain, therefore x1 doesn't really
I
influence
remind you
x0.
something. It's not a Markovian chain.
Yeah.
In the forward, in the reverse, it is a Markovian chain, because from xt, I'm going to xt minus 1, and from xt minus 1, I'm going to xt minus 2, etc. It's just that I need to provide you with x0. So what do? I do the same cheat that DDPM did. I'm replacing x0 with a denoised version of xt. And
I
so
see.
in the reverse, it is a Markovian chain, but not in the forward.
Mhm.
Okay?
Thank
So coming back to this table, let's look at the last line here. Look, in CIFAR 10 and Celeb A, they tried 10, 20, 50, 100, and 1,000 steps. With 1,000 steps, you get terrific FID, the best. Okay, but if you start increasing the number, decreasing the number of steps to 100, you start losing quality very fast. In fact, in Celeb A, the speed with which you lose quality is horrible. With 100 steps, you are already in 45, which is poor-looking images. Okay, now look, let's go now to the top line. Let's go to the top line, these elements here. With 10 steps, you are with FID 17. Not great images, but okay for 10 steps. For 20, it's 13 or 14. For 50, it's 9. So basically, for 50, you're already getting results that are comparable to what you will get here with 500 or 600. For 50, 9. For 106.53, definitely good quality images. Not as good as this one, but okay ones. And so this is the game that DDIM is providing. Notice that DDIM with eta equals 1 shows also an ability to reduce the FID quite substantially, even for 100, but it is better always to use eta equals 0. It is always performing simply just better. You see, the bold numbers are marking the best in each column. Okay, and we have seen this. And here are some generated results as a function of eta. For 10 and 100 iteration, this is CIFAR, and for 10 and 100 iteration, this is Celeb A. As you can see, for eta equals 0, 10 steps, and you already get good-looking images. The same here and here. In fact, the images you get for 100 or for 10 are almost the same in quality, as opposed to what happens for the last row that refers to the last row here. Here you get basically noisy images that you cannot look at. It doesn't show any content. Or here, after 100 steps, it starts to be okay, but it is quite heavy with noise. So not the kind of images you want to get. Okay.
Mickey, can I ask a question?
Yes, please.
You've mentioned that when choosing eta to be 0, we achieve the best results, optimal results. But isn't when eta is 0, isn't the model deterministic? What if we want the model? What if we want the model to not have a deterministic quality?
Well, it is deterministic in the process that starts from xt all the way to x0, but xt itself is random. Okay, so by changing the vector xt, you do have randomness if you want one, and you do want one. So every vector, every initial vector of noise will create another image, and we'll talk about it in a second. You'll see where it helps.
Okay, thank you.
So this is DDPM with 1,000 steps, images from CIFAR. This is DDIM for 1,000 steps, and this is DDIM for 100 steps. The thing I want to draw your attention to is the fact that the images with 100 or 1,000 steps of DDIM are nearly the same in quality. In fact, they're not just the same in quality. Look, they are the same period. This is a car, and this is the very same car. This is some sort of an animal, and this is the same animal, etc. And why? Because if you start from the very same vector, and this touches on the last question here, if you start with the very same vector x capital T, and you do either 110 or 100 or 1,000 steps, you end up with almost the same image. Okay, so knowing xt dictates what is the output image. So this is why all these images here are the same as all these images here, and the quality 1,000 versus 100 nearly the same. Okay. And the same here, what you see here is the Celeb A results of DDIM for 20, 50, 100, and 1,000 steps. As you can see, if they started with the same vector, they get the same lady all the time, the same person all the time, just with slightly better and better quality that is influencing FID by 1, 2, 3, etc. Okay. Now let's talk about this interpolation that I kept mentioning. Here is the thing that you have to understand. When you would choose eta equals 0, DDIM becomes deterministic, as I said. What does it mean? It means that every initialization x capital T is mapped to a specific image in the output. This is very much different from DDPM. In DDPM, if I start from this point and I run the algorithm several times, I will end up with different images. DDIM, on the other hand, for every starting point, it will produce only a single specific image. You can run it 1,000 times with this vector, it will come back to the very same place. Why? Because there is no additional randomness, okay? Apart from numerical issues that we might neglect. Okay, this is some sort of benefit, and I'll tell you why. Imagine the following. Imagine that I take a random vector xt and create this image. I take yet another random vector xt, a different one, obviously, and I'm creating this image. Now I can create a mixture of those two vectors, xt1 and xt2, okay, those two random vectors, create a mixture between them. It's a convex combination of some sort, and I can now generate images all through the passage from one vector to the other, and I'm getting intermediate images. And so I'm interpolating images. I'm getting a sequence of faces that are smoothly varying from this person to this person, or from this bedroom to this bedroom, or from this church to this church. And why church? Because there is a data set of churches and there is a data set of bedrooms. In fact, here is something even stronger that you can do. There are some papers that talk about reversing DDIM. If I give you x0, an image, any image, can you tell me what is the noise that generated it in DDIM? Turns out you can reverse DDIM. And why is it important? Because now I can take two arbitrary images, find their initial vectors xt's, do the interpolation and get interpolation of the images. So this is something that can be done as well. Here is an illustration of the same thing. 4 images in the corner were generated using 4 arbitrary xt's. And now by mixing these vectors in all sorts of ways, you can basically move in this 2D plane of faces, changing from this person to this person, from this person to this person, etc. The same goes here for churches, 4 churches and some churches in between. Okay. This was DDPM. Questions so far?
Nick, how do you reverse the DDIM?
I didn't dive into those algorithms. I know that it is being done.
I see.
But I never really dived into the specifics of how it is done. No.
Okay. Thank you. Yes.
Other questions? Okay, so let's have another part and then have a break. Let's talk about denoising diffusion GANs. This is lighter. Okay, and I'm referring to this paper, tackling the generative learning trilemma. By the way, the drawing I show you at the beginning with these 3 blobs that talk about precision, recall, and speed, this is taken from this paper, a paper that came from NVIDIA. Carsten Kreis is well known, the same with Arash Vadat, well known in the field of diffusion. They are the authors of several key papers in this field. And in this paper, they are offering the combination of GANs within diffusion in order to speed up diffusion algorithms. And this time, the speed up is obvious. We know exactly what we are after, and we are going straight at the target. Okay? So I'm going to discuss it, and later on, you will see that there is some resemblance between what they do and what nested diffusion, the work that Noam Elata did, is promoting, even though there are delicate changes and, in fact, motivations that are coming from different angles. So let's see this work. How do you accelerate DDPM? The obvious thing to do is to use coarser betas, not betas that are very, very close to 0. Choose larger betas, and so you will, instead of having 1,000 steps, you will have 100 steps. Okay. You know, if you do that, the forward path will not be compromised. It will be just as good. The migration from xt to xt plus 1, etc., it will be smooth and clean, and the noise will be added elegantly. It all will be perfect. But the reverse will be horrible. The reverse will not collaborate. And why? Because in the reverse, suddenly a fundamental assumption is being broken. What is the fundamental assumption? Anyone? What is it that's going to break here? what is it that we assume about the reverse that suddenly may not apply?
But you have small steps, and so the reverse is Gaussian.
Exactly it, exactly. So let's see how this plays. So they are suggesting a conditional GAN in order to overcome this problem. So what is a conditional GAN? You will see in a minute. And here is what they are saying. If betas are large, this probability that goes backward is no longer Gaussian. And so two things happen. First, you cannot hold it as a Gaussian with mean and covariance. And secondly, if it is not a Gaussian, how do you sample from it? So instead of coming up with this expression and then sampling from it, let's overcome all of this in one way, one block of conditional GAN that simply gives me a sampling. How does it work? In a minute. Okay, but here is a motivation that will illustrate what's happening here. Imagine that we have the forward process that moves from x0 to x1 to x2 all the way to x5. Okay, I'm stopping at x5. As you can see, the densities are smoother and smoother as we move to the right, and rightfully so, because we are convolving with a Gaussian, right? In fact, if we go all the way up to x capital T, we'll end up with a pure Gaussian. Lovely. Now imagine that for the game that we are playing now, I'm standing on x5 and I'm wondering about jumping back to x4. The conditional probability of x4 given x5 looks like a Gaussian, which is exactly what we did. This is fine. The conditional of x3 given x5, that means if you want to jump straight from x5 all the way to x3, the conditional here starts to break the Gaussianity assumption. In fact, if you do a larger jump to x2, the Gaussianity is totally broken. It's not true anymore. So clearly, you cannot keep the algorithm as it was in DDPM and keep assuming Gaussianity and work with it, because it will give you something that is distorted. So what do you do? So here is what they suggested. In fact, here is what they did not suggest. I'll show you something simple just to illustrate what can be done, and then I'll show you what they suggested. Okay, so here is the idea. Remember, the game here is the following. I'm standing on xt. I'm about to jump to xt minus 1. Unfortunately, the distance between xt and xt minus 1 is such that Gaussianity of p theta here cannot be assumed. And I would like to find an alternative. And I remind you what we are after. We are after a sampling from this distribution. I don't care what this distribution is. I don't need to get an expression for it. All I need is a sample from it, because I need to give you xt minus 1 hat. Okay, so here is what we can do. You can take many, many good-looking images, x0s, and create the forward path of the DDPM with crude betas. This is fine. We know that it works. And now you will have many, many examples of how xt minus 1 and xt look one versus the other. So take many, many such triplets. M here can be 100,000. Take such triplets of time t, the image at time t minus 1, and the image at time t. And now let's train a machine that generates straight a sample from this. How? It looks like this. Here is the generator. This generator is a miracle machine that will get xt. It will know the time t, and it will generate xt minus 1, something that aims to be a sample from this distribution. Okay, we have here an extra input. This is a seed vector, a random vector. This random vector makes sure that if you change it, you keep getting all sorts of other samplings. Okay, so this is a randomized machine. Good. So you have xt minus 1 hat. How do you know that this is a valid sample? What you do is to match it with the xt minus 1 that you do have in your examples. You feed it to a critic, sometimes the true xt minus 1, sometimes the generated one. And if the critic can tell you which is which, by the way, the critic itself is also getting xt. So it knows the context, xt, and it tries to look at xt minus 1 that we are suggesting versus the true one and say which is which. If it can tell me who is the synthesizer and who is the real, then it really means that the generator is doing a poor job. And so with the loss, I can squeeze more force into the generator up to the point where those xt minus 1 hats will look better and better and competitive. And now you have xt minus 1, keep going. So basically, instead of applying a denoiser, they apply this generator that moves us from xt to xt minus 1 hat, and that's it. And now, instead of running DDPM with 1,000 steps, run DDPM with, say, 5 steps. 5, 4. This is actually the number they are using. And in every step, you call this machine that gives you the next jump of xt minus 1 given xt, which is a sample. This is something they could have done. They wrote about it in the paper and said, this is not what we want to do. Here is what we will do. And it will remind you of how DDPM works. Here is what they did. They took the triplets I mentioned, xt minus 1 and xt and the time, but also involved the original image x0. And here is what they did with these. Okay, it's a conditional GAN with 2 layers. This generator is getting exactly the same inputs, xt and a seed vector of random values and the time t, and it has to produce x0 hat, a sample of the clean image. Okay, this clean image is fed to the probability density function that we are familiar with. Remember, DDPM had a closed form expression for this horrible looking conditional. So take it and just insert, instead of x0, insert in this expression x0 hat that came from here. I remind you, epsilon t, x0 are interchangeable. So you can squeeze it, and here you draw from a Gaussian. This is an analytic step. And now you get xt minus 1 hat. And this is the one you compete with the true one. In fact, I'm not sure they did it. If I had to plan this machine, I would have had 2 critics. One that compares xt minus 1 to xt minus 1 hat, and one that compares x0 hat to x0, the true one. And so I would like this to be a fair sample from the image distribution, and this will be a fair sample from the image distribution after t minus 1 steps. This is the conditional GAN they trained, and it works. And let me show you how well it works. Okay.
So Mickey,
Yes.
the critic here, does it need the time step as well?
It might need. I'm not sure about the detail. I'm guessing it will need it. It needs to know what it is working on. Why not? Yes, I would push it here as well. Other questions? Okay, so here are some results. What they show here is a graph that shows the FID as a function of how long it takes to generate images for CIFAR10. For CIFAR10, I don't think they have results for ImageNet, which is problematic. And this is them. This is their approach, which is so much better than all the diffusion techniques. Okay, although each of these is a diffusion method that existed at the time, and this is their approach that basically says that in a fraction of a second they can generate an image. Here is DDIM, the green. DDIM, the fast version that we have just learned about. It is working well, but it can be improved by an order of magnitude with their approach. Okay. By the way, for CIFAR10, they are not competitive with this element here. Who is it? This is style GAN. This is a GAN that gives excellent FID and excellent speed. This is yet another style GAN. This is SN GAN. So various GANs are very good at CIFAR10. I think that if a similar graph could have been created for ImageNet, then we could have seen that GANs are no longer in the game. And then the FID that we get with diffusion techniques or with their approach probably is better. Here is another slide with some results, just to show you the flavor of things and how people are comparing things. So what you see here is their approach, Denoising Diffusion GAN, T equals 4. 4 steps. Inception score, FID, their FID is 3.75 for CIFAR10. This is their recall, typical number, 0.6, roughly speaking. NFE is neural function evaluation. Basically, how many denoising you apply, or how many neural networks are you running. In their case, it's the generator, which is a neural net that does denoising. I remind you, their machine that produces X0 is a denoiser. It's a randomized denoiser. So with 4 application of denoiser and with something like 1/5 of a second, they get this FID. All these are diffusion method. Look at DDPM just for example. DDIM exists here. Let's look at DDIM. DDIM 50. FID is 8.78. No, sorry, this is DDIM shows an FID of 4.67. Slightly worse. The recall is slightly worse. 50 activations, 4 seconds. Okay. DDPM runs 1,000 denoisings, takes 80 seconds, has a lovely recall and a better FID. Okay, just illustrate. These are some GANs and these are alternative method. Look at the alternative method. All their FIDs are horrible, apart from the last one, VAE BM. Okay. I I think this is a great time for recess. Let me pause. Okay, we proceed now with nested diffusion. Lovely idea, work that was done by Noam Elata together with Bajat Kawar. Let's see what this idea is. So here is the paper. Noam Elata and Bajat Kawar, together with Tomi Mikhail and myself, came up with this notion of nested diffusion. It's a speed-up algorithm, but not so much a speed-up algorithm as something we choose to call anytime generation. By anytime generation, we mean that the generation process might be long, but already in the very beginning, you will already see good-looking images, the kind of which you can expect to get at the output, so that you know where you go. And so you can stop if the process, you can trade quality for speed. Lovely approach, somewhat related to the previous work with GANs. Let's see how. In fact, I would like to start with something very basic in probability that kept confusing me, and I would like to highlight it because it is critical for our story. Imagine the following. Imagine that there is a probability density function of A and B, two random variables, and this is their joint probability density function, okay? You know, A and B could have been vectors, but just for the sake of simplicity, let's assume that these are scalars. Now the question is, how do you sample from P of A? This is my goal here. Sample from P of A. What does it mean? Regularly, it means that you have to marginalize PAB to remove the dependency on B by integrating over B. Get a 1D probability density function, and then sample from it. Now, this is not something I would like to do. So I'm going to sharpen my question. Imagine that sampling from B is actually easy. How do you get a sample from A? And the answer is relatively simple. Here is what you have to do. It's a sequential sampling. And it says, here is what you have to do. You can sample from B. Go ahead and sample. Go ahead and sample B star from the probability B of P of B. Okay, so you choose a very specific B star that is a fair choice, fair sample from P of B. Given this B star, look at the conditional P of A given B star and sample from it. So what am I doing here? Instead of integrating as I did before, I'm taking an intersection, just the function over this line, and I'm sampling over it, and I'm getting this A star. And so I got A star, B star. And if you throw away the B star, you end up with A star. A star is what we were after. This is the claim here, okay? It's not a proof, it's a sketch of a proof. The idea is the following. This A star and B star, according to this regime, is basically a fair sample from PAB. Why? Because of the very simple formula that says that P of the joint AB is P of the conditional PA given B times PB. And so reading loud the equation here on the right, it says, first PB can serve you in order to choose how B should be sampled. And so this is exactly what we did. And then you plug it into the other part and choose A. And so choosing sequentially B and then A is exactly choosing a pair from the probability, the joint AB. And once we have them, forget about the B, look at the A, and you're looking at a fair sample from PA. All this might seem trivial, not to me anyway, and yet it is something that we used quite intensively without even noticing. Let me show you where we have used it in our previous meeting. In fact, all diffusion relies on it. I remind you what we do in diffusion. We want to sample from P theta of x0, the learned probability of true images. We want to draw images from this distribution. But you don't have access to this distribution. What do? You do have access to the probability of the complete path. And luckily for you, this path is Markovian. And so it has this multiplication that says, draw at random xt, x capital T. This is a Gaussian, just do it. Plug it into this conditional and draw at random xt minus 1. Plug it into the conditional and draw xt minus 2, and so on and so forth, all the way to x0. And once you finish, you throw away all the elements and remain with x0, and this is it. It's exactly what I've just shown you. So when we do this sequential sampling, we are essentially sampling from the joint and throwing all the elements apart from the last one using this sequential strategy, okay? So this is something we relied on, and now I'm going to use it once more in a more delicate way. So let me remind you what diffusion algorithms in general are all about. This is what they do according to this equation. You start by drawing at random xt, x capital T, and then you run downwards this expression, this conditional, and you keep drawing at random one vector at a time given the previous one that was sampled. You do this, you sample. Luckily for us, these are considered as Gaussian in most cases, so we know what to do in order to sample them. And we end up with a chain of xt's all the way to x0, and then we forget about the line of xt's, take the last one, and this is our solution. This is a typical diffusion model. Okay, now how is it that we do it in DDPM? We do not work this way. We don't have such a formula. So let me show you the explicit choices we have made in DDPM. First, yes, we assume that p theta is Gaussian, which is a great assumption to make. If it is true, this is great. Why? Because it's easy to sample from Gaussians. Okay, so this is one step. Secondly, we developed an expression for it. The expression is with a specific mean and a specific variance. The variance is simply a number times identity. The mean is a combination, linear combination of the currently held xt, this xt, and x naught that is taken from a denoiser. And we sampled from this. So here is what we did. Here is the actual algorithm that corresponds to what I've just described. Look at what we do here. You draw at random the first vector as a Gaussian, just as usual. You draw at random just a canonical vector z. You compute the mean that I've just shown you, a linear combination of the denoised image and xt with proper coefficient. Multiply this random vector z by a constant that the formula suggested, and this will be our sampling from p theta. Okay, so when we say sample from p theta, this is what we mean. Okay, but there is something delicate here. This choice of using the denoiser is annoying and delicate, and I would like to highlight it and zoom in on it. Okay, so I'm going to change the way I'm presenting the algorithm a little bit without changing anything. Here is what we do. I'm coming back again to the same story. You sample a Gaussian vector, and per each step, you take the currently held vector xt, you compute the conditional mean, basically a denoiser. You apply a denoiser, you compute the mean of that Gaussian with that denoised image, add some noise with proper coefficient, and this is your algorithm. Okay, so this is an MMSE denoiser. It doesn't have to be MMC, but it will be some sort of a good performing denoiser. And this is the actual sampling from this Gaussian that we are familiar with. Great. Now the question I would like to zoom in on is this conditional mean or denoiser in general. Why? Where is it coming from? So from the practical side of things, here is what happened here in order to give birth to this denoiser. Here is what happened. We wanted very much to work with the reverse Q of xt minus 1 given xt, but we didn't have access to it. There is no closed form to it. And so we cheated. We added an expression, we added to the expression the knowledge of x0, and suddenly this has a closed form. Okay, this has a closed form, and so what we did is to say, okay, let's have this expression with its closed form as close as possible to the p theta by matching the moments, and then when you call for x0, just replace it with x0 hat, and you feel that someone is cheating here, and the question is, how severe is this cheat? So again, let's zoom in on this step and understand what exactly we have done mathematically speaking. Here is what we have done. This is the expression we want to work with. This is the expression we had to work with because it is accessible. What is the relation between them? Marginalization. If you take this expression here and integrate over all the x0 given xt, okay, with their probabilities, then you remove the dependency on x0, and this is the mathematical way, the proper way of removing x0. Now, this part is a Gaussian, closed form Gaussian. We know this to be a fact, and this is exact. Terrific. What about this? What about this? What is this? Can you tell me in words what this conveys?
It's an MMC denoiser.
Is it? Let's think about it. I'm giving you a noisy
Posterior.
image. The image xt is indeed a noisy image, and I'm asking what is the probability of x0? What do you think? Is it going to be a delta function?
No, it has some various distribution. Like
What would you expect the center of this distribution to be?
This is MMSE, no?
MMSE will, or let's say a denoiser, seem like a good choice for being the center or the mode of this probability. But is it going to be so narrow as to assume that it is just delta? Can we assume that? I mean, if I'm giving you a noisy image, is there only one way of cleaning it up and saying this is the result, forget, there is no uncertainty here? Could it be? The answer is no, of course not. And yet, here is what we actually did. We assumed that this is a delta function. We assume that this is a delta function around the denoised result, okay? And being a delta function integrated with this simply says, take this expression x hat and replace it here. When you convolve a Gaussian with a delta, it's basically a Gaussian where x0 is replaced with where the delta is vivid, is existing, okay? So basically, we have simply assumed that this has zero variance. But this is wrong. And this is why we use denoising as our way of going from this expression to this expression. The interpretation is, let me tell you, you are thinking of this as a delta function, but it is not. Now, the question is, can you do something better? So people struggled with it. All sorts of papers came up with all sorts of ideas of how do you bypass this assumption? Here is a new way of thinking about things. Here is the expression we wrote before, the very same expression, this marginalization. This is what we want. This is what we have. We have this, and we have to marginalize with this unknown probability in order to get to this, okay? And here is something truly delicate but brilliant that needs to be understood here. You don't care about this Q. Sorry, just before that. This multiplication is basically the joint probability of xt minus 1 and x0 given xt. I hope you see that, okay? Now, coming to the delicate issue. The delicate issue is that nobody cares about this probability. We don't need it. What do we need? We need a sample from it. All I want is an xt minus 1 sample that will be a fair sample from this distribution. So how do I get such a sample? I go to this joint and I sample sequentially. I sample x0 first, and then I sample xt minus 1, and then I throw away the x0, and I keep the xt minus 1, and that's it. What am I telling you? You don't have to do any integration. You have to do sampling. You have to sample x0 from this distribution, and you have to sample xt minus 1 from this distribution where you plug in x0, the sampled one, inside, just like what we did a few slides ago. I hope that this is clear. Okay, so this would be the strategy that we need to follow. Okay, by the way, yes, please.
How do I exactly sample x0 from the first distribution?
This is exactly the topic of the coming 3 slides, okay? But since you asked, let me tell you, if you think about it, the diffusion plus GAN that we have just seen did exactly that. It produced x0 hat, sampled, and then it plugged it into the Gaussian, sampled from the Gaussian, so they followed the same rationale without even noticing that they are doing the proper thing, mathematically speaking. And yes, the question is, yes, please.
So do you need like a probabilistic denoiser where you estimate something other than the MMSE?
Yes. If you take the denoiser, you are not sampling, you are hitting the center, but you need a sample. So you need something slightly different, and it's quite delicate, but it is different. So the sequential approach, sample from x0 somehow, and then plug it into the Gaussian and sample from this Gaussian. Now, this is the easy part. We know exactly what to do here. What do you do about that? Okay, so the previous work did that by a GAN, a trained GAN. Okay, and we will do something different. So just to summarize, if this is the regular algorithm that computes a denoising, it could be an MMSE denoiser, and then plug it in the mean in order to come up with a Gaussian from which you sample, then I'm telling you, you have to replace this step with a sample. If you do that, you are more accurate mathematically speaking. Okay, and yes, the question is, how do you sample? So instead of GAN, Noam Elata and Bajat Kawar said to themselves, just a minute, what is the best known sampling technique for sampling images from distribution? Diffusion. So let's use diffusion. So let's replace this line with yet another diffusion algorithm. Okay, this is the nested diffusion. So it's a diffusion within diffusion. And here is the algorithm. Don't be alarmed. It's very simple. All this block is a diffusion algorithm, standalone diffusion algorithm that starts from xt, does constant S steps of the regular diffusion with the nasty assumption that you can use a denoiser and then sample from a Gaussian. When you finish, you get Z0. Take it as your X hat 0, plug it into here, and the outer loop knows exactly what to do. Okay, so you have S steps inside and T steps outside. Notice that the outside diffusion doesn't have smart things to do. All he has to do is to get some vector X hat and plug it into a Gaussian and sample from it. So it's the inner diffusion that does the work. Okay.
But isn't it a problem that you still have the MMSE inside?
It's less of a problem because now it serves yet another task, and we will see what happens. Okay, and you can imagine a nested diffusion where you can replace this with yet another diffusion, and I don't think we tried. Okay, so altogether, this algorithm will have T times S steps in which you apply denoisers. So in order to be fair, when I compare a vanilla algorithm to the nested algorithm, I need to make sure that the number of NFEs, we call it, NFEs, neural function evaluations, is the same. So S times T for the nested should be similar or equal to the overall number of steps in the vanilla algorithm. And we will see that we make sure that this is exactly held. We call it anytime image generation because after every S steps, you can look at X0 and it looks great. It doesn't look perfect, but it definitely looks much better than the usual X0. And in fact, let me show you some results to illustrate what I'm talking about. If this is a vanilla algorithm that runs for 250 steps, only in the very last steps, you get a crisp image. This is what you get in the nested. In the nested, already in the beginning, after 50 steps, you start seeing good-looking images. Why is it different? Of course, it's different because the process is randomized. So it has to be different. So the same with this image where you hardly see anything for 150 steps and only towards 200 you start seeing something. Here you see it from the beginning. The same here. In fact, here is an illustration. Well, after 50 steps, you get this blurry image. This is what you get from the nested. After 150, you get this blurry image. This is what you get from the nested. After 250, you get two images that are comparable in quality and of course different. Again, it's stochastic. In fact, here is a way of comparing things in a very elegant way. Imagine that I'm running an algorithm that has 200 steps, 200 vanilla steps. So I'm looking at the X0s as they are created along the time, and I'm computing their FID. And look, the FID is so horrible all the way to 150, and then starts decaying towards the final results, which is quite good in FID, something like what, 2, 3, something like that. This is for ImageNet. This is the vanilla algorithm. In green, what I'm showing you is the nested diffusion, the outer loops. The outer means after 40, 80, 120, 160, and 200. I'm looking at the X0s that the algorithm produce. And as you can see, already after 40 steps, we get FID that is truly competitive. The results are truly ones that you can look at the image and decide whether you want to stop or not. The bluish part here is the algorithm with the inner steps included. So basically, you start from the same place. You run the inner loop, get a very good image or reasonably good image, and then you leave it, add a lot of noise. This is the outer step, and keep going down, and keep doing back and forth all the way down. So this is the FID as a function of the number of evaluations of the denoiser. Here are some more results. This is from stable diffusion. Stable diffusion is something we will talk about a lot next week. Stable diffusion is a diffusion algorithm that can take a text and turn it into an image. So in this case, the text was a photograph of a nest with a blue egg inside. What you see here is the regular stable diffusion, and the one that nested suggests. We're using the same number of steps, 100 altogether. After 25, you already get good-looking result. The same for this, a photograph of colors diffusing in a martini glass. You wait for 75 steps and still get horrible results, only to get this at the end. This is what you get from the very beginning, and so on. Yes.
I didn't catch something in the previous slide. So let's say I want to run the outer loop only once. So the inner algorithm already after 50 loops gave me a very good result. So what is the inner algorithm doing different than some vanilla algorithm?
If you run only once, you get to this FID. If you
yeah, but it's
excuse
good
me.
enough here. Like
If this is good enough, stop here. But if it is good enough, this is yet another regular diffusion. This path is nothing but a diffusion algorithm that ran for 40 steps and gave you something. So this is by itself not nested. This is just applying 40 steps and stopping here.
Why is the vanilla one not getting here also after 40 steps?
Oh, the vanilla is not running so crudely. Remember, we are running crude. Maybe I should come back to the algorithm here. If this is the algorithm, the parameters betas and alphas that govern this algorithm are different. They are cruder. They are creating large jumps because I'm giving you a budget of only 40 steps to finish the process. Okay, so you have to cope for that. Okay, we proceed to these images. Two more examples of stable diffusion. You squeeze a text and get an image that match to it. You get it quite good from the very beginning, or you wait a while to get it. Again, more graphs. This is for the ImageNet generation, not just for 200, for 250, for 200, for 150, and for 100. Let's take, for example, the 150. So this dark green is the regular vanilla algorithm. This is the FID of it. And the light green is what you get with the nested if you jump 30, 60, etc. Okay? So it does show the benefit. You see the line curves here compared to the ones that are up there. This is COCO results. COCO refers to the experiment we have shown before, where you have text and you want to match the text to the image. And you can see the results of the nested are definitely always within a good FID value. This is where I stop with nested, and I'll move to the last topic of today's lecture, covering several other acceleration techniques. And with this, we will finish. Okay. So what we have seen so far is the DDIM, which removed the Markovian nature of the forward and removed the stochasticity and turned into a deterministic algorithm. It was sufficient to move to something that is working faster. We saw Diff GAN and we saw nested diffusion. Both of them basically sample X0 smarter. And because of that, they better handle this conditional that goes reversely. But these are not the only approaches. And there are several, many other papers that do all sorts of things, even simpler things. So let me crudely mention those in order to give you the complete picture. Okay, so there is definitely some work that suggested multi-scale synthesis. So basically creating the images in growing sizes makes a lot of sense. There is an option of working in the latent space. This is exactly stable diffusion. We'll talk about it towards the end today. And the most recent comers to the game are consistency and distillation techniques that deserve a chapter of their own. And simply because it is a very new topic, I have not yet prepared such a chapter, but I do want to mention them to let you know that they exist. So what I'm going to do now is to briefly discuss every one of these. I'll start with the first, move to the third, and then talk about stable diffusion. Okay, look at this paper published in 2022, not far ago. Cascaded diffusion models for high fidelity image generation, basically work that comes from Google. It's a team from Google that sits in Canada, if I'm not mistaken, yes, Canada. And basically what they are suggesting is, let's read the abstract. We show that cascaded diffusion models are capable of generating high-fidelity images on the class-conditional ImageNet generation benchmark. Let me explain. Class-conditional means I'm creating an image, but I'm also dictating that it has to be a dog. I want to be a cat. It has to be an airplane, etc. So we'll talk about this next week and see how it is done. This is not crucial for our understanding. A cascaded diffusion model comprises a pipeline of multiple diffusion models that generate images of increasing resolution, beginning with a standard diffusion model at the lowest resolution, followed by one or more super resolution diffusion models. Let's stop here and see what they say. So basically, here's the idea. You want to generate 256 by 256 images? Don't. Start by creating 32 by 32 images. This is so much easier. The denoiser is much lighter. You can run many iterations and it hardly costs you anything. And once you finish, take this and use it as initialization in order to create a bigger image and a bigger image. And every time, model 1, model 2, model 3, each of them is a diffusion model, a complete diffusion algorithm that takes you from one image to the next. The first model is a classic diffusion. It's a diffusion. Yes, it has an input that says, give me the class. So in this case, iris setter, so I need the specific dog, okay? But I'm generating an image. Once the image is generated, I'm taking it and I'm asking, what is the bigger image that corresponds to it? This is a super resolution problem. This is exactly the topic we will talk about in the last chapter, 2 weeks from now, when you talk about inverse problems. So we increase the resolution. Here, specifically, they inject the knowledge about the class to the next models so that the image insists on remaining relevant to this class. This is the idea. It has been practiced a lot with GANs before, and it is being practiced in Imagen. We'll talk about Imagen next week. So it's a lovely idea, and it's simply one that works, so simple to apply, and it is a speed-up approach. Okay, this is one thing. Distillation and consistency. Honestly, this is a rich topic with a lot of results, all of them nearly 1 year old. The older papers are not as competitive, but the ones that were published in the last year are simply amazing. And let me tell you what they do. They take the diffusion process and squeeze it into one network. One network does everything. And so with activation of something like one denoiser, you end up doing the complete synthesis. So we are training a sort of a denoiser that takes you from X capital T all the way to X0 in one step, or you know what, in 3 steps, 4 steps, that's all. And it works. And I'm showing you a bunch of papers that do this. Knowledge distillation in iterative generative models already in 2021, but again, the performance was not competitive, so nobody took care of it. Then fast sampling of diffusion models via operator learning. Arash Vaadat, we have seen the name. Consistency models by, look at this paper. This is the paper that brought the attention. Yang Song, I mentioned his name. Yang Song is the other Song that worked with Stefano Ermon. Yang Song, after PhD, worked in OpenAI for several months. And so he's collaborating here with Ilya Sotskover and others and Darival in OpenAI and published a paper that basically says, we can do diffusion in one shot. Consistency models. On distillation of guided diffusion models, yet another paper, in this case, Rombach, that we'll see the name in a second coming up in the context of stable diffusion. He is part of Stability AI. Stability AI is a company from Germany. Tim Salimans, Ho, are people from Google. Stefano Ermon, we have seen the name. So it keeps coming to the same name. Chening Meng, we have seen his name as well as a student at Stanford University. So basically a mixture of people from Europe and Stanford and Google. Okay, so these are the papers. And indeed, this deserves a chapter of its own. This is where I stop. Okay, let's talk about latent diffusion. This is the paper that was published, what, 2 years ago, April 2022. Published by a group from a university in Germany and a company, Runaway Machine Learning, which eventually turned into Stability AI. And what they are offering is something truly technical. Do diffusion in the latent space. So basically apply a variational autoencoder, get a representation, and do all the diffusion in the representation. Why? Because the representation is shorter. You have condensed, you have reduced dimensionality, and now we can do things faster. And this led to something called stable diffusion. And stable diffusion is famous. Everybody are using it. And why? Because it is nearly the only software for diffusion that is shared freely. And so people can use it, and not just shared freely, it is one of the sophisticated techniques that can generate images from text and from all sorts of other conditioning. And so this explains why they are heavily cited. Now, honestly, if you open this paper and read it, it's one of the most boring papers you ever seen. It's completely technical. It has no news. It's basically piling of technicalities in order to create something that truly works better. Okay, but their code is shared, and this is a major strength. Okay, so how does it work? Here is a picture that keeps appearing everywhere, and this is a picture from their paper. Looks horrible. Here is what they say. You have an image X. Push it through an encoder. This is encoder, this is decoder. Push it through an encoder. Turn it into a vector that is shorter. This is the latent vector. Now do the forward diffusion, the assumed forward diffusion. You start from a vector of content and slowly it turns into a Gaussian. This is the forward process. In the reverse process, you start with the Gaussian vector in the latent space. All this horrible square here is a denoiser, a specific Q-net denoiser with attention. So you apply denoising again and again and again, up to the point where you get a proper Z, then feed it to the decoder and come back to a good-looking image. The dark lines are suggesting all sorts of conditioning. You can condition the synthesis of the image on semantic map, on text, on representation, on images, all sorts of things. And so this is the machine that converts those entries into something that the machine knows what to do with. This is the algorithm. Now let's zoom in on it a little bit. So the prime element is the autoencoder. They are not using regular variational autoencoder because we know it doesn't really work well. So they use either VQ-VAE or VQ-GAN, two kinds of VAEs that are smarter with adversarial loss and a different way of capturing the representation in the latent space in a more expressive way. In fact, VQ-VAE is such that if you look at the vector at the output of the encoder, it has spatial meaning. So you can apply all sorts of convolutional networks on it just as if it was an image. And this is critical. The size of the vector here at the outside is smaller by factor 4 in each axis. So basically you work with much smaller data, and so you can gain speed. Okay, the latent representation has spatial interpretation, and therefore the inner denoiser is convolutional, and rightfully so. Okay, this is the process of diffusion. It is applied on the latent. This is all I wanted to say here. And the denoiser is trained. You train a denoiser of different kind. It's a denoiser that works on those strange vectors, not images. The denoiser itself is a unit with attention. I don't have much to say about it. And in the attention itself, it can get all sorts of conditioning, class conditional synthesis. For example, create a specific breed of dogs, and you can get these. Or here is a sentence. Please create an image that matches this sentence. Sounds like a miracle. We'll talk about it next week, and we'll see how it is done. Or layout. Just give me a rough layout of the image, and I'll create an image that matches to it, etc. So beautiful things can happen here, and it really works well and fast. This is why everybody are using it. And this is stable diffusion, the most famous, one of the most famous diffusion techniques known today. This is where I stop today's lecture. Let me stop the recording.